Okay, so for our next problem, looking at centripetal forces and uniform circular motion, we're going to take a look at another real-world situation. Now, what you may not have noticed, we talked about highway off-ramps in one of the previous problems, where that's a highway and you have an off-ramp that goes up something like this. If you were to look at those from the side, that's supposed to be an eye, so you're looking at it from the side, they're actually what's called banked. They actually make an angle, so the road's slanted a little bit. And you'll have a car on it like this, where we're actually looking at either the back or the front. That can be the grille of the car, windshield wipers. There we go. So in this case, it's coming towards us. Now, this angle, well, it's not just willy-nilly. They could actually level everything out. In fact, when they construct things, they usually do. So why is that slant there? Why is that angle there? Well, normally when you go around a corner, so in a car, like in our first problem that we took a look at, the car is able to go around the corner because of friction between the tires and the ground. You can imagine if it was iced over, it's hard to turn or control your car in general if you hit a patch of ice. So, it's normally friction that lets you go around a turn. Well, the reason that these highway off-ramps are banked this way are to help account for wet conditions. Maybe if it's raining, or if it's snowed and iced over. That can severely reduce the friction, possibly even get rid of it altogether. And so what they've done is they've set up these banks in a very strange way, but a very smart way. Those banks, that angle, is in there on purpose. And they're usually designed either to be exactly or very close to, taking into account real-world situations, the angle that you would need to actually make the car go around this curve, even if it doesn't have much of any friction. That's one of the reasons why, whenever you approach one of these, they have a speed limit sign on there. And it's not always the same speed limit. It's something like 30 miles per hour or 25 miles per hour is a common one. 40 miles per hour on some of them, but those are usually much bigger ones. All right, so what we're going to take a look at here is something where either you're designing this and you're putting in a bank of a specific value based on how big your turn is and your velocities, or conversely, if you've got a bank that you're taking advantage of, you can find out exactly what speed you want to put on that speed limit marker for people to take that exit at. Okay? And so what this is doing is, if you take that exit at that speed, at say 30 miles per hour, even if it's rainy and wet and you don't have as good of traction between your tires and the road, there's still a good chance that you're going to come through it just fine. So in order to find this, we're going to have to take a look at a free body diagram. I've got my free body diagram here, so here's my object, my car. It's got mg down. We've got some normal force up like that. See, just like we've done before. Now in the past, one of the things that we've done is we've actually tilted things where we declare our x-axis to be down the hill. In this case, we're not going to do that. We did that before because if there was any motion in that direction, we kept track of it. In this case, if we look from above, we see that we're actually going in a circle. So we're experiencing some acceleration, a centripetal acceleration, directly to the right, in our old classical positive x direction, straight to the right. And we'll have an up of plus y. In this case, just like before when things were physically moving, I would make it where all of my acceleration is in one of those dimensions. It makes my math much easier. Well, this time, I have an acceleration. It's not me speeding up or slowing down, but it's an acceleration because I'm constantly changing my direction. And it's going to be in this circle. Well, that circle, the center of the circle, is directly to the right of the bank here. So it's actually level here. It's not down into the earth like we might see over here. I'm not going into a circle where I dive down into the earth and come back out on the far side. No. My center is actually on level ground. And because of that, I want all of my acceleration to be in one dimension. My centripetal acceleration, this acceleration that's making me go in a circle on the surface of the Earth, well, my center of it's going to be on the surface of the Earth. So, It's going to look a little bit different than we've done before, but it's not a big deal. In this case, I'll have my sum of forces. Let me divide up my forces into components. In this case, because I'm using the classic plus y up plus x to the right, I have a component here and here for the normal force. I've got this theta here. We know we've seen this before. That theta corresponds to this. If you're confused by that, double check. And by geometry, this angle is going to be theta as well. So here and here. Okay? If you need to, go ahead and pause the video. Make certain that you understand why those angles are the banked angle that we have here. You can do the little hand trick that I do in class if necessary. Okay, so if I do apply Newton's second law, as we have many times before, my sum of forces in the y direction, I've got my normal force times, well, here's my angle. This is my y component. It's going to be my cosine. Normal force, cosine theta, because all of my normal force, some of it points off in the x, some of it points off in the y, so I'm going to find the component, this guy here, that points in the y direction. There's another component in the x, and then those go along like that. So, the component of my normal force in my y direction is the total length of the normal force, the total value of it, times cosine theta, minus the other force there is mg equals, well, I've got no acceleration in the positive y. It's not sliding up or down the hill. I set this up so all of my acceleration, my centripetal acceleration, is in the x direction. So this is going to be may, which this guy is 0. So I end up with, well, let me do my sum of forces in the x direction. Sum of forces in the x direction, I've just got one component of the normal force, so I'll have normal force, in this case it's opposite side, so I end up with sine theta equals my mass times my acceleration in the x direction, which is my centripetal acceleration, because I'm going in a circle. Okay? So, if I take a look up here, I know that my acceleration in the y is equal to 0. I can add my force of gravity to both sides, and I end up with my normal force times cosine of theta equals mg. I can find for my total normal force by dividing cosine from both sides. mg divided by cosine theta. Alright, so I take a look at this. I've got normal force times sine theta equals my mass times my centripetal acceleration. I'm going to take my normal force and put it in, because I know that it's equal to mg divided by cosine theta, so I'll have mg divided by cosine theta times sine theta equals mass times centripetal acceleration. My masses cancel out because I've got a mass on both sides, as they often do. That's why it doesn't say, hey, there's a given speed limit if you're a semi-truck and a given speed limit if you're a Volvo. No, with the mass canceling out, for the most part, this is irrelevant based on the size of the car. Okay, well, I'll end up with g times sine theta divided by cosine theta equals my centripetal acceleration. Well, sine theta over cosine theta, g tangent theta, that's an identity. I'm just going to simplify that a little bit, equals my centripetal acceleration. And then finally, from what we know from before, our centripetal acceleration equals v squared over r. All right, so I'm going to set this equal to v squared over r. And I've got a relationship here. I've got g tangent theta equals v squared over r. Now from this, I can actually decide what I want to find, because this is one of the upsides of not having plugged in any numbers. In fact, I haven't really generated any numbers yet. This is a general equation. This applies pretty much all the time. As long as my drawings are accurate, then we're in good shape. So I could go in, and I could use this and say, okay, well, if I want the size of my, I know that the size of my off-ramp has to be, what were my sample numbers on here? I've actually got a few. So if I have a radius of, if I've got a situation where the radius here of my off-ramp is, we'll go with 40 meters. Okay, and I know that I want them to take this at 25 miles per hour, so I'll go with a V of 25 miles per hour. I realize that that may be cutting it off, so let me see, I'm running out of chalk here. V equals 25 miles per hour. If I convert that to meters per second, it's 11.2 meters per second. So I've got the physical size of my off-ramp. I know the velocity that I want them to realistically take it at. I could plug those in. I could plug in 40 meters down here and 11.2 here, square that, and then solve for my theta. I would end up with theta equals v squared, the inverse tangent of v squared over gr. So this is a way that if I know my physical dimensions and how fast I want them to go, I can figure out what type of angle I want to bank it at. And for that case, theta would equal 16.5 degrees, which is a pretty realistic value. There are other ones that I could do where I could instead say, well, I know that there's a rough bank that I've already got put in, some theta, and I know the size of the off-ramp. Usually that's something that you have to kind of figure out because you've got a specific space you have to put it in. If I had a situation where I had this where theta, my bank, was 17.7 degrees, and the size of my off-ramp are... Oh, I'm sorry. I read totally the wrong number. In fact, this guy, for the one that we talked about there, was 17.7 degrees. If this, instead, very sorry about that. So, if it's 40 meters in radius, and we want to take it at 25 miles per hour, 11.2 meters per second, we would have to bank it at about 17.7 degrees, which is a little high. Most likely what they would do is they would have a slightly larger off-ramp. If we had a situation where we had an angle built in already of 16.5, we're taking use of something that was there, pretty much, and we had a radius of 110 meters. That one's a much larger circle, you can imagine, but the velocity that we could do that one at is 17.9 meters per second, which is about 40 miles per hour. And so when you see the bigger off-ramps, sometimes they're ones where you merge onto another highway. You have a situation where it's like that, you go onto another highway, and the speed limit here is something much higher. It's usually like 40 or maybe 60 miles per hour. So you don't have to slow down much because you're leaving one highway going on to another. Well, if you look at it, the radius, if I were to draw this into a full circle, would be a very big circle indeed. And that's where we end up with this 110 meters, for instance. Okay? So, these are general equations that we ended up solving for, and you can see by doing just a little bit of math, we can solve for either theta, we can solve for our speed, we can solve for how big we need to make the off-ramp. Okay, so we could solve for any of those, and we could evaluate where we want to put things in to see what our speed limits were, how big it needs to be, the angle that it's at. And all of this is built around trying to make certain that if it's rainy or frozen or anything like that, that you're not going to have people go sliding off of the off-ramp and ending up in a ditch somewhere. That would be unpleasant. So, whenever you're driving and you're taking one of the off-ramps, be certain to follow the instructions that it says on the speed limit. Okay?